pretty low cost of production. In terms of biofuels, if you could turn cellulose, which is this long thing here, into biofuels, you've got access to a lot of capacity without impacting food crops because of agricultural waste and waste from pulp and paper production and various other sources. So with cellulosic biofuels, you could actually offset an awful lot of gasoline and still use liquid fuels for transportation with all the advantages they have, and far more capacity than with grain-based biofuels because of the limitations of how much of the food we can turn into fuel. Now, that's a great thing to say, but there's a lot of work to be done in terms of the crops and optimizing them so that it's easy to get at the cellulose. This is not something that comes naturally. Cellulose is the structural material of the plants. It's designed to resist attack. It's a polymer chain of sugar, and the sugar is what you want, but nature has engineered those systems to make them resistant to attack because they're what holds the plant together. So you have to overcome that, although we've already seen that there are, even just within the biodiversity that exists now, strains where it's easier or harder to access that cellulose. And possibly with genetic engineering, you could optimize around that. Enzymes and pre-treatments that would allow you to efficiently get at this. I think my pointer died, so I'll just keep going without it. Eliminating some of the steps, and the other thing you've got to deal with is that different food stocks are suited for different regions of the world. So sugarcane happens to work pretty well in Brazil. There are lots of other places where it's really doesn't make any sense to try and grow it. Some countries are well suited to trees, and so if you had a wood-based method, that would work. Particularly in northern latitudes. There are in the tropics. There are a lot of more oily plants that you can imagine using. So you're actually probably going to have a suite of options for biofuels, just because of the geographic and the variation in climate around the world. Fossil fuels still represents right now, as I said, 80%, and there's no scenario where you eliminate that quickly. It's too big a shift. And so for that reason, it's really important to look at options for mitigating at least some of the CO2 emissions associated with fossil fuels, because they're going to be with us for at least another 100 years to some extent. This is particularly true if you start looking at things like cold liquids to deal with transportation fuel and offsetting petroleum. These processes generally use a lot of water. They are very energy intensive, so there's CO2 emissions just associated with getting to the point where you have a fuel that you then burn with further CO2 emissions. So that actually increases the need for carbon capture or ways of using it for other purposes so that it's not released. There's about 21 projects as of February of this year for demonstration projects for large-scale carbon capture and sequestration. Many of them involve the use of CO2 for enhanced oil extraction, pumping the CO2 into the ground to get more oil out. The reason that's attractive is because essentially the CO2 is valuable, so there's a value proposition where you can make money by pumping it into the ground. But it also becomes a way of just understanding what happens when you do that. How stable is it? How long does it stay there? So that's what a lot of these demonstration projects are around. And it's because of the cost and the energy costs associated with doing it that you're seeing most of those deployments being around enhanced oil extraction, because otherwise it's just a net drain on the economics. But hopefully these types of projects will allow us to understand whether or not it's really viable. Now this is a tough problem. If you imagine taking all the CO2 emissions associated with fossil fuels, assume you could separate it into a clean CO2 stream, which is not what comes out of the coal-fired plant. That's nasty stuff. You've got to separate out the CO2, compress it to the density of water. Right? and then that's what you're going to pump into the ground. The volume of material you have to deal with then is equal to the total volume of petroleum production around the world. So roughly speaking, that means you've got to dump as much. It's not surprising, right? You've got to put as much back into the ground as you took out of it in some sense. And so the infrastructure associated with that is going to cost as much as the infrastructure associated with getting it out in the first place. So this is, this is a tough one. You've got to get to gigaton levels for it to work. So although I think it's important to work on this, particularly as we think about the near term where we're not getting out of fossil fuels anytime soon, I think we have to be kind of cautious about assuming this is going to solve the problem.